In this video, I would like to present one final rule called the Law of Cosines that can help us solve additional non-right triangles. Without proving the Law of Cosines, I would like to present it in three different forms. A squared equals b squared plus c squared minus 2bc cosine of a, or its two alternate forms are provided below. You will notice that in all of these forms, the side length we are solving for on the left side corresponds to the angle measurement that we take a cosine of on the right side. The two other lengths are used in these places in the equation. So the law of cosines can be reformatted in three different forms depending on which information about the triangle that you have or what you are trying to solve for. We can use the law of cosines to solve triangles where we know two sides and the included angle. We call that an SAS triangle, or all three sides but no angle. We call that an SSS triangle. Adding in the law of cosines gives us more power to solve additional kinds of triangles. Let's use the law of cosines to solve the following triangle. And I'm going to label everything for clarity here. We'll call this angle A, we'll call this angle B, and angle C. Therefore, what we have is side length A equals 10, side length C equals 12, and we don't know side length B. So what we're looking at is a side angle side triangle. Notice that we know a side length, an included angle, and another side length. Let's use one version of the law of cosines to solve for the remaining side length. So I can say b squared equals a squared plus c squared minus 2ac cosine of b. Or b squared equals 10 squared plus 12 squared minus 2 times 10 times 12 times cosine of 30 degrees. We can simplify this somewhat, but at some point we'll have to go to a calculator to round this answer. I have b squared equals 100 plus 144 minus 240 cosine 30, or b squared equals 36.153. When I take a square root of both sides, I get approximately b is equal to 6. Depends how many decimal places you want to use here. That might affect other answers further on down the line. If I'm rounding to one decimal place, I'll get b equals 6.0 or b equals 6. Now let's go on, and we still need to find two missing angles, angle A and angle C. It doesn't look like I can use the law of sines here, except in its ambiguous case, which I'm trying to avoid in this scenario. So let's set up the law of cosines one more time. And let's say I want to solve for angle C. Here's what I know from the law of cosines. C squared equals a squared plus b squared minus 2ab cosine of C. Now remember, the unknown here is angle C. So I'm going to need to do quite a bit of rearranging and then take an inverse cosine in order to solve for C. I have 12 squared equals 10 squared plus 6 squared minus 2 times 10 times 6 cosine of C, or 144 equals 100 plus 36 minus 120 cosine of C. If I simplify this further, I'm going to get the following equation. 8 equals negative 120 cosine of C, or dividing by negative 120, cosine of c equals negative 8 over 120. Now, how do I solve for angle C? Well, let's take an inverse cosine. If cosine of C equals negative 8 over 120, then that means the inverse cosine of negative 8 over 120 equals C. As long as we're talking about an angle C between 0 and pi, this will work. Now C has to be between 0 and pi here because we're solving a triangle. C must be some angle between 0 and 180 degrees. So when I find the inverse cosine of negative 8 over 120, using my calculator and rounding to one decimal place, I get C is equal to 93.8 degrees. So I have a solution for angle C, and that also came from the law of cosines. Now we can quickly find the missing piece, angle A. Angle A equals 180 degrees minus the two other angles that we've already found, 93.8 and 30 degrees. And so, in short, we have angle A equals 56.2 degrees. Remember that because of my rounding earlier on in the problem, depending on how you did your rounding and what steps you took for your problem, you may see slightly different answers here for angle A and for angle C.